Hello everyone, and in this video, we're going to be talking about a strategy that can immediately solve this IMO problem here. This was from, I believe, 2008, and here's how it goes. Suppose that H is the orthocenter, the intersection of the altitudes of the triangle ABC, and M, N, and P are the midpoints. And then we draw the circles with center M, N, and P, and passing through H. And then they intersect at A1, A2, B1, B2, C1, and C2. And what the IMO asks the contestants to prove is that all of these points lie on the same circle. A1, A2, B1, B2, C1, and C2 are all concyclic. So it might seem really hard to prove it at first, because if we try angle chasing, then we'd have to relate some of the points with other ones that we not want to, and things will become a lot messier unnecessarily. However, there's another method that can be used to prove that points are cyclic, as we will see. And then there's a concept called radical axes. So let me go ahead and spell it out on screen. Radical axes, which can trivialize the problem. So without further ado, let's get started. So first, what are radical axes? So suppose you have two circles here, omega 1 and then omega 2. Well, the radical axis is a set of all points, P. Suppose that there's a point P here, and then this is O1 and O2, such that the power of point P with respect to omega 1 is equal to the power of P with respect to omega 2. And the question is to find what the set of points P that satisfy this condition is. And the circles do not have to be intersecting, by the way. And the cool thing about this is that the set of points ends up being a line, which is really interesting. But exactly why is it a line? Well, we'll see how. So this proof is the easiest one. So suppose you have the two circles in the coordinate plane, and then you have another circle here, suppose. And the centers all lie on the x-axis. So this point here is, suppose, t0, and this point is the origin. And without loss of generality, suppose that this point here has radius 1. This circle here has radius 1. So this circle here and this circle has radius r. So this circle here has equation x squared plus y squared equals 1, as we know by the Pythagorean theorem. And this circle here has the equation x minus t squared plus y squared is equal to r squared. And we want to find out what the set of points P that satisfy that the power with respect to each circle is the same. So what we can do is draw the lines towards each one. So this is, suppose, point O and then point X. And then the power with respect to this circle here is equal to OP squared minus, suppose, the radius squared, which is 1. And we want it to be equal to XP squared minus the second radius squared here, r squared. But how can we compute OP? Well, if P equals AB, then we can use the distance formula. OP here is equal to A squared plus B squared, so that's minus 1. And then PX here is equal to A minus T squared, because it's A to T, and then B squared, so A minus T squared plus B squared minus r squared. And you might see why we're using coordinate plane here, because the b squares cancel out. So now we can just expand this to get a squared minus 1 equals a squared minus 2at plus t squared minus 1. And surprisingly, the a squares also cancel. And this is actually an r, sorry. And surprisingly, the a squares also cancel. So those go away. And then we are left with 2at is equal to t squared minus r squared plus 1. So t equals, so that means that a is equal to t squared minus 1 plus r squared plus 1 over t. And since a is an x coordinate, this formula here just tells us the set of points that the x coordinate must satisfy. So this condition here is necessary and sufficient for p to lie on for p to have the same power with respect to each circle. However, this represents the equation of a line that is actually perpendicular to the line connecting the radii. So we are done. And know what happens here? If the two circles intersect, then if this point here is x and then this point here is y, then the radical axis is just xy, as you see, because the power of x with respect to omega 1 is equal to the power of x with respect to omega 2, which is 0, because x lies on both circles. And similarly for y. And since 2 points on the line define the line itself, we get the radical axis. So without further ado, let's get going to the problem. So the goal that we want to prove is that all of these points are concyclic. So how can we go ahead and do this? Well, considering our radical axis idea and also power of a point, we know that BC2 times BC1 equaling BA1 times BA2 implies that all of these points are concyclic. A1, A2, C1, C2 by power of a point converse. Well, what does this mean in terms of the two circles? Well, BC2 times BC1 is equal to BA2 times BA2, but this is just the power of with respect to this circle, suppose omega 1, omega 2, and omega 3. However, we want to then prove that the power with respect to omega 1 of B is equal to the power of omega 3, with respect to B as well. So in other words, we want to prove that B lies on the radical axis of this. However, the radical axis here, if this next intersection point is x, then this radical axis is just hx. So we now wish to prove that x, the second intersection point, lies on hb. In other words, we want to prove that b, x, and h are collinear. So how can we get started on this one? Well, by the radical axis thing that we noted here, all the way up this over here, we note that it's just the a equals that. So the radical axis is actually perpendicular to the line connecting the two centers. So that means that hx is perpendicular to MP. However, we know by midpoints that MP is parallel to AC. So that implies that HX is perpendicular to AC. And this is definitely something because we also know that BH by definition is perpendicular to AC. So, but BX is perpendicular to AC. So that means that all of these points lie on the same line. And then we are just done by applying power of a point on B. We're not done really, because we just proved that A1, A2, C1, C2 are concyclic. One can similarly prove that B1, that C1, C2, B1, B2 are concyclic, and B1, B2, A1, A2 are concyclic. We want to prove that they all lie on the same circle. So how can we do that? Well, We want to consider where the center of the circle is. That's the key thing for the problem. So the center of the circle C1, C2, B1, B2, here's just the intersection of the perpendicular bisectors. So something like that and something like that. So suppose that's the point O. So that's the center of this circle here. However, this means that O here is a circumcenter. In other words, the center of the circle circumscribing ABC. So that means that OM must also be perpendicular to BC. However, this means that O is also the center of each of B2, B1, C2, C1, A2, A1, C2, C1, and C2, C1, B2, B1. It's the center of this all possible of these red circles. Therefore, since we have all concyclic points and they share the same center, we must have that all 6 of these points are concyclic, as we need.